Hello and welcome to our screencast, Temperature Compensation of Load Cells with an External Compensation Resistor. My name is Ralph Emberger and I will guide you through this screencast. What you will learn in this screencast is the theory of the PICOSTRAIN temperature compensation. This includes the full compensation and we will have a look how this is done in practice, as well as the only offset compensation, and we will also see how this is done in practice. So coming to the theory, we first will have a look at a classical Wheatstone bridge and how the temperature compensation is done there. It is done by the use of gain compensation resistors, here namely Rspan 1 and 2, and offset compensation resistors R(1) and R(2). So a whole network of resistors is needed to compensate for temperature, and this means also to make a lot of mechanical adjustment and that the load cell cannot be fully assembled before doing the temperature adjustment. So coming from the classical approach, we now have a look at the PICOSTRAIN temperature compensation, which is somehow easier in its approach because it's only using one Rspan compensation resistor, and the gain and offset adjustment is then done by feeding the chip with some register setting, and an internal algorithm will do the temperature compensation. So in total there's only one gain compensation resistor needed, and it can be adjusted after the mounting of the entire cell. Having a look at the PICOSTRAIN measurement principle, we see that it is based on discharges from a capacitance over the strain gauge resistors, where the Rspan 1 lies in one arm of the full bridge, meanwhile the other arm of the full bridge has no Rspan. This way we can determine in terms of time the size of Rspan and also correct it that way. That means by setting some registers and doing some internal multiplication, we can basically adjust the value of Rspan very accurately. On the other hand, the offset adjustment of the bridge can also be done by the chip. Since the chip gathers information about each and every half bridge, it can calculate the offset between the two half bridges, and with a dedicated offset compensation register we can then balance out the offset over temperature. To sum it up, the PICOSTRAIN temperature compensation is done mainly by two chip internal parameters, namely Tk gain and Tk offset, where Tk gain is to correct the gain drift by the use of Rspan, and Tk offset is for correcting the offset drift. So since we know now the theory of the PICOSTRAIN temperature compensation, let's have a look now how this is done practically. In practice, independently whether PICOSTRAIN technology is used or not, there are principally two ways of temperature compensation which are applied. The first one is the full compensation, where gain and offset drift is compensated for with each and every load cell. The second method is to take only a sample out of a lot and make the full compensation there, and take the obtained values for correcting the gain and applying this for the rest of the lot, and doing only the offset compensation for each and every load cell separately. Of course, both ways are possible with the PICOSTRAIN temperature compensation. However, as the latter method is prevailing in practice, we are now focusing in our explanation on the second way of doing it. So let's have a closer look at possibility 2, where we can assume that we have a lot of, let's say, 5,000 load cells to compensate for temperature, and out of this 5,000 you take, for example, some samples out, let's say 10 pieces, and determine the proper gain correction factor for these samples. This is done by the full compensation, and then afterwards, from the correction factors obtained of the 10 samples, you can calculate an average correction factor. So for example, load cell 1 would have a Tk gain of 0.95, load cell 2 0.96, 3 0.94, and so on. So at the end you sum them up and calculate the average, which would be here in this example 0.95. So this is your gain correction factor applicable for the whole lot. That means also for the rest of the lot, here 4,990 cells in this example. You can then use the average Tk gain setting for the whole lot. That means using the same gain correction factor for all the load cells. In PICOSTRAIN we can do this very comfortably since the TK gain is only a factor to write into a register to make the gain correction active. So we call this gain correction over the whole lot. It assumes load cells with similar properties and temperature behavior. And we also recommend to do a verification of proper gain drift behavior with some further samples out of the lot. Since the offset drift of each load cell differs, there's the need to compensate for it individually, done by only offset compensation. So to sum up, the only offset compensation method individually compensates for the offset of each load cell. Meanwhile, the gain drift is compensated for by adopting the TK gain values of only a sample and apply this to the rest of the lot. So we then now come to the practical part of the screencast, where I first will show you how to prepare the hard and software for doing the measurements. After having installed the driver and software to the PC, you can then plug in the PicoProc version 2.0 programmer to your load cell. Once this is done, we are good to start the software. Starting the software, in this example PS09 software, you will be asked for firmware to download to the PicoProc programmer, which you can select here in this upcoming window. And then it's recommended to do a first communication check by clicking the buttons Power Reset, Download Configuration, Init Reset, and finally Verify Interface. Another window will pop up then and tell you the status of the communication, like here shown OK. On the measurement sheet you then can set some characteristics of your load cell. For example, here the full scale of display, which would be the maximum capacity. Here I put in 10,000 grams since it's a 10 kg load cell. And then you can write here the sensitivity of your load cell in, for example 2 millivolt per volt. By clicking Start Measurement, the measurement will be started and you can see very quickly if it works or not. This is recommended to do before going to the temperature compensation sheet. Some further settings are need to be made on the ALU page here. We focus on the compensation factors field, which is here below. And since this screencast is about the use of load cells with an external Rspan, you first need to deactivate the internal Rspan checkbox. This is an option only available in PS09 and described in a separate screencast. If you want to know how to use the internal Rspan for temperature compensation, please refer to this separate screencast. Of course, the Apply Rspan Correction checkbox should be activated, and then later we need to set the TK gain and TK offset values to their standard value, which is 1 for TK gain and 0 for TK offset. This way we are prepared to start with the temperature compensation procedure. Please note that the recommended settings in this screencast are related to a sensor, which is the PICOSTRAIN full bridge, and not a Wheatstone sensor. So if you want to use a Wheatstone sensor, there are some differences in the settings, which are detailed explained in our white paper 2. And the practical implication in the software here would be that you select a Wheatstone configuration. I just load a standard Wheatstone configuration here. And you then can see that the TK gain is adapted from 1 to 0.75, which is needed for doing the temperature compensation with a Wheatstone sensor. So once again, please make sure if you use a Wheatstone sensor to adapt the configuration accordingly. Having everything prepared, we now come to the full compensation, which is the compensation of both the gain and the offset drift. For this purpose, please put the electronics and the load cell inside a temperature drift chamber and then set first the lower temperature, for example 10 degrees Celsius, and wait a settling time of at least 1.5 hours. This is to make sure that everything inside a temperature drift chamber has the same temperature. Once the settling time has passed, we can then start a temperature compensation procedure by first writing again 1 for TK gain here in this field and also to the TK gain reference field. before filling in then the lower temperature to the temperature field here, in my case this is 10.1 degree Celsius, and then I start a measurement by clicking this button here. The measurement will be started then, and the measurement values are changing in this field up here, so they are automatically taken by the software and filled into the blue table. After the 4 first measurement values, the 5th one is with applying load. A message is indicating that, and then you can put on the load to the load cell, which should be minimum half maximum capacity. And after that the measurement procedure for the lower temperature is finished, and this will be acknowledged by another message, and also by the green field saying performed in the blue table. So now the measurements for the lower temperature are done. Having the measurements performed at a lower temperature, you can then set the higher temperature in the temperature drift chamber, for example to 40 degrees Celsius, and wait again the settling time of at least 1.5 hours. After the settling time has passed, we repeat the procedure for the higher temperature. First we fill in the temperature in the dedicated field and say then start measurement. Again the software automatically takes the measurement values and fill it in, this time in the orange table. For the last measurement, again it is necessary that you put on some load on the scale. And after this measurement is done, there's another pop-up window telling you to remove the load from the scale, and after doing so, the TK gain and TK offset values are calculated automatically and shown in these fields here. You can then store additionally the values to the Rspan by clicking this button. After having obtained the TK gain and TK offset values, there's basically nothing more to do than store those values to the Rspan of the load cell. However, we want to give you some remarks about the TK gain value. Basically, the TK gain value is to adjust for the gain drift of the load cell, and this is done by adjusting the value of Rspan. With a gain setting of 1.0, it means that the Rspan in its value is fully taken into consideration. That means if you have a 40 ohm Rspan, for example, then this 40 ohms will be taken into effect. However, if you want to modify this value, for example reduce it by 10%, you could set 0.9 for TK gain, and you would obtain then a value of 36 ohm for a Rspan. If the load cell to adjust had formerly an Rspan, the value for TK gain is normally expected to be around 1.0. Sometimes the load cell formerly had or still has a parallel resistor to compensate for the thermal nonlinearity of the load cell. In this case, we recommend to keep the parallel resistor, or in case of PS09 you can also emulate a parallel resistor. So let us have a closer look at the parallel resistor and the thermal nonlinearity. First of all, it's important to distinguish the ordinary nonlinearity from the thermal nonlinearity. The ordinary nonlinearity refers to a nonlinear behavior over weight, meanwhile thermal nonlinearity refers to nonlinear behavior over temperature. We refer in this explanation to the thermal nonlinearity. On the left hand side in the picture you see a circuit where Rspan is paralleled by another resistor Rp, a parallel resistor. This can be a physical resistor or a virtual resistor like the emulation of PS09. On the right hand side you see then a diagram which is showing with the blue curve the nonlinear behavior of a load cell over temperature. Since the Rspan paralleled by Rp is also having a nonlinear behavior over temperature, but which is acting in the opposite direction, we have some counteracting towards the nonlinearity of the load cell. So overall we get the red curve showing a smaller nonlinearity, a smaller overall nonlinearity of the system by this effect of the parallel resistor. Now that you understand the meaning of a parallel resistor, I will explain you in which cases it is recommended to activate the emulation of a parallel resistor within PS09 or to solder or keep a physical parallel resistor on Rspan with PS081. The three cases are: first, the determination of TK gain gives a value smaller than 0.8, or second, the temperature run with TK gain of 1.0 shows a gain drift bigger than 100 ppm per Kelvin, and third, the load cell formerly had a parallel resistor for thermal nonlinearity correction. For details of how to configure the parallel resistor within the chip, please see the datasheets of PS09 or PS081 respectively. In this last part of the screencast, we will focus on the only offset compensation. In contrast to the full compensation, here the TK gain value will not be actively determined, but only the TK offset value. Having a look at the former slide, we can recall that by taking a sample of a load cell lot, we can determine the average TK gain setting, which is then applied to the rest of the lot. This way, the gain is already adjusted. Practically, this means to take, for example, 10 load cells, determine the average TK gain, and write this to the register of the rest of the load cell lot. Then the only offset compensation is still to be done. This is what this part is practically about. In the software, you first select offset compensation only and fill then in the TK gain reference value. In line with the former example, I fill here in 0.95, which will be all measurements be made with then in the following. You can fill then in the lower temperature, for example 10 degrees, and start a measurement by clicking the button. The measurements will be automatically taken and the values will be filled into the blue table. At the end, there will be a green field coming up and saying that the measurements were performed successfully. Having the measurements performed at a lower temperature, you can then set the higher temperature in the temperature drift chamber, for example to 40 degrees Celsius, and wait again the settling time of at least 1.5 hours. At the higher temperature, the same procedure is repeated. So first of all, you fill in the temperature. In my example here it's 40.2 degrees Celsius, and start then the measurement by clicking the corresponding button. All measurements will be done automatically and filled into the orange table. Once all measurements have been taken, a green button saying performed again will indicate that all measurements have been taken. Then the TK gain and TK offset calculated values will be updated in the left button corner. Of course, the TK gain will be the one you set earlier, and only the offset value will be updated. You can then additionally store the TK gain and TK offset values in the way you know already by clicking the Store TK gain TK offset button. So that is all that is needed for doing the only offset compensation, and as you saw, this is a very comfortable way to make the offset compensation, since there's no need to charge a load cell and no weight needs to be applied. Well, we reached now the end of the screencast, and I want to say thank you for watching. Feel free to visit us on our website, where we provide some further information around PICOSTRAIN. This includes further screencasts, for example the one about temperature compensation using the internal Rspan, which is available with PS09. So please feel free to visit us, and thank you for watching again. Bye bye.